Hey everyone, so this video is going to be on the whole concentration ratio and how to draw those like membrane transport graphs. So the first thing I'm going to start off with is just really basic, what is this concentration ratio? So actually that's not what I wanted. So this concentration ratio we defined as the concentration of like some molecule X inside the cell, or like you could do this with anything. So inside versus the molecule, or the concentration of molecule X outside. So I know that this isn't math, but it is important for the purpose of biology to be able to like quantify stuff. So what we're going to say is that when this ratio, so I'm going to lay out like three conditions. So I'm going to say this is like xi and xo for outside and inside. So when this concentration is equal to 1, that means that xi is equal to xo, right? So that means that the concentrations inside and out are the same. So concentrations same, which means that there is no concentration gradient. And this is really important because when we're talking about passive diffusion, right, we mentioned that for passive diffusion, so this includes facilitated and simple diffusion, the gradient is the driving force. So if we don't have that gradient, there is like no gas in your car, nothing is really going to make things move in such a way that like concentrations are going to equal like out. Like you're not going to have everything suddenly moving inside the cell or everything suddenly moving outside of the cell, because that wouldn't make sense. There isn't that driving force. What you will have though is you will still have diffusion occurring. So things are still moving in and out, right? Because we have to remember that it's a dynamic system. So things are still going to be moving in and out, but really we want to remember that generally that ratio, that concentration ratio is going to stay around 1. So the other two conditions are greater than 1, which means that xi is greater than x naught. So the concentration inside is greater than the outside concentration. And then, of course, we have less than 1. That's not good. Less than 1, where x naught is now greater than xi. So the concentration outside is now greater than inside concentration. So I think the next thing I'm going to touch on is just like the basic idea of those graphs. So I think the first thing that you'd want to focus on is, or would want to like set up, is drawing your axes, right? Your x-axis is time, and your y-axis is this concentration ratio. So I'm just going to say concentration of x in versus concentration of x out, where x is like whatever molecule that you're looking at. And then a great thing to do would be to draw some kind of line representing 1, because it also just gives you perspective to know where, like, what's going on. So I'm going to start with a scenario where the concentration inside is greater than the one outside. So I'm going to start somewhere up here, some random value, but what's important is that it's greater than 1. And right when we said greater than 1, we were talking about how that meant that the concentration in was greater than the concentration out. And I'm going to draw my graph like that. So in drawing my graph like that, and in showing that there's quite a bit of time where it's plateauing and not passing 1, I'm really describing passive diffusion. And remember when I said up here, I was talking about how really what's going on is that at the beginning you have this quite strong gradient, right? Your concentration in is larger than that outside. So there is a driving force for things to move with the gradient. So like down their gradient, down like a slide, right? They want to move along the gradient. So the molecules will start to move from a high concentration to a low concentration. But remember that that doesn't mean that molecules won't move in the other direction, right? Motion is happening in both directions. But the net movement, so actually I'll label it, so here, net movement is out because things are moving down the concentration gradient. But things could still be moving in, so just keep that in mind. And then really I'd like to like zoom in on this area and think of this line not so smoothly. So really there's like these fluctuations of things constantly moving in and out, right? So even though you're like really close to, I mean, you can essentially just like draw this going to 1, but we want to think of things always moving. It's a dynamic system. Stuff is like always moving in and out. Whereas if I'm going to draw, here I'll choose a different color. If I'm going to draw another curve starting at the same concentration, but maybe something like this happens, then I've clearly passed 1. So in the beginning, I'm going with my concentration gradient, right? Until I pass 1, the concentration in is greater than out, and things are moving out because my ratio is getting smaller, right? When my ratio is below 1, we know that the concentration outside is greater than inside, so things are moving out. But once I've passed 1, now what happens is that I'm actually moving against the gradient, right? I'm not plateauing at 1 anymore. I'm clearly pushing, like pumping things in the opposite direction. I'm really actively trying to lower my ratio, the concentration ratio, and things are being pumped outside. So this is active diffusion, and really clearly the main idea is that because you're passing 1, you have this period of time where this is with the concentration gradient, and now here, like this whole time, you're against concentration gradient, right? Because your gradient would actually want to push you in the other direction. If you're pumping things outside, now there's more outside than inside, so things are going to start flowing in, but you're using energy to physically move things outside because that's where you want things to go, or that's where the cell wants things to go. So that's really the main idea here. But like I said earlier, I mean, I could have, so I'm going to erase this. I could have started at any concentration, right? I just started at like an arbitrary concentration. I could have started here and drawn it going like that, which is an example of passive diffusion, right? Because I'm going to 1, or I could have drawn it like this or like that. And so these two would have been examples of active, right? This is passive. So there are many ways to represent the curves, but really the main idea is that you just need to clearly show that if it's active, it's going to pass 1 if you have that information, because things can pump, like you have those protein pumps that can make the concentration ratio greater or less than 1, and you aren't constricted by this fact that when you get close to 1, you don't have the concentration gradient anymore, so things are going to have less of a driving force to move, whereas in the active transport, as long as you have ATP, right, that's really important. ATP is needed for active transport. So as long as you have it, you have this ability to pump things in the direction that you want to and past that leveling off at 1.